Our last speaker this morning session is Forrest Meggers. Forrest has a joint appointment with the School of Architecture and the Andlinger Center for Energy and Environment. Professor Meggers is a native from Iowa. He had his bachelor's degree in mechanical engineering at the University of Iowa. I understand his goals were then to go into bicycle engineering. And Jerry Schnorr is a close friend and was listed as our second speaker on the highlights series, saw something in Forrest and told him to aim higher and convinced him to get a master's degree in environmental engineering and then a PhD at ETH Zurich in architecture. After that, Forrest spent 3 years in Singapore with the Singapore National University, working in energy efficient buildings, and he's now at Princeton running the Chaos Lab, which has sort of a nice ring. It stands for cooling, heating, architectural systems. He'll tell us more about it.
Yes. Thanks, Peter. So very, very much. And yeah, thanks to everyone for being here. I know I'm the last thing between you and lunch. So, of course, what I'm going to do is provide toys. So, I have a couple of little devices, and during my presentation, this is one to play with because I'm pretty sure my live demo just quit working due to Murphy's Law. So your objective is to figure out how the thing that we rapidly prototyped will eventually replace that thing, which is much more fun. You can point it at your friends, see how hot they are. You know, you'll see when you get it. Higher? Sorry. Okay. Everybody can hear me? Not scratching around too much? Okay. So, let's... Oh, you all know who I am now? How do you build a bridge? I don't really know, actually. I'm not a structural engineer. And as you can tell, bridges made out of styrofoam are probably a pretty bad idea. And we'll get to what this bridge made out of styrofoam is a little bit later. But what I wanted to talk about today, right, is the analogy of the bridge that I try and create in my role, jointly appointed between architecture and engineering. And this is my chance to thank Emily as she goes on to bigger things, but hopefully we still continue to maintain that bridge. And thanks to her for taking a risk, appointing a chaotic person like myself into the center to have a role in this environment in architecture, as well as in our fantastic new Andlinger Center. So today I'll talk about how I try and make that bridge by looking at applied design through the lens of fundamental science. And the challenge, one of the fundamental challenges, is how you really span the rhetoric between these two places. And as you heard about my background, right, I started in Iowa and wanted to be an engineer and design bicycles, and then all of a sudden got interested in buildings and their efficiency and went to New York and worked for Jim Hansen. So the talk yesterday really hit home about the emissions component of buildings, which is really what drove me to study them. And the challenge now, though, is how looking at the state of the planet, as we heard yesterday from Ralph Cicero very eloquently, there's a big challenge, and I think buildings are one of the places that are pretty obvious to start making some of those changes. So today, I'm going to walk through first that issue of why buildings are important to me and why they're maybe bad. But they're also good, hopefully in the end, as we'll see, through new concepts and ways to leverage engineering thinking in architecture and the idea of chaos, and how we can then do projects that, through integration, create that bridge across these two silos of engineering and architecture that often seem so far apart. So why buildings? Well, the obvious answer is that if you look at the data from the DOE, 75% of US electricity is utilized in the building sector, and around 40% of all the CO2 emissions is attributed to buildings. So that's a pretty easy motivation. But the problem is when you look at this big Sankey diagram of where all the energy goes in and then ends up producing carbon dioxide, yeah, cars are pretty easy. Oil in, cars drive, and boats and planes. It's pretty straight across. But buildings are everywhere. Buildings are part of the energy sector, right? There's not actually one thing on the left that says buildings, right? And there's residential, commercial buildings, there's agricultural aspects that involve buildings. So really it spans all these different places. And so in order to really address that, we have to think both holistically and integratively, right? So we have to think about opportunities that really span particularly disciplines. And that's why I think bridging as a theme for the talk today is something I hope we can all relate to and how we can address this problem. And not just in the context of disciplines and areas, but also in terms of climate change and the ideas of mitigation and adaptation, right? Because buildings are large generators of emissions, as we just saw in the statistics, but they're also the parts of our infrastructure that are most vulnerable to things like temperature rise and sea level rise. And I think one of the funniest feedback loops that are pretty obvious, if you think about climate change, right, is I have to understand how buildings lose and gain heat. And so when the temperature starts to rise due to climate change, that changes how we design buildings, which changes how much electricity they use, which then changes the CO2, which again changes the climate change. And so this whole loop and understanding how buildings play a direct role in all of these different aspects of climate change is really critical. And at the end of Ralph Cicerone's talk yesterday, we had this slide of the bell curves with the extreme events right at the high end of the temperature scale. So what is the worst case scenario? And I think in the context of our built environment and urban spheres, what you see here is Southwest Asia, the area of the United Arab Emirates. And one of the fascinating things that comes out of the data when you look at what happens in the end of the century is in the high emission scenarios, we have places on the planet, that whole purple section, the temperature there is above what you can physically survive, because the wet bulb temperature, right, similar to the dew point temperature, is the point at which your sweat doesn't evaporate anymore and your body can no longer cool itself down. So extended periods of time outside in these zones are no longer inhabitable by humans, right? So the only way to live there would be in some crazy, hyper-futuristic, indoor air-conditioned environment. I don't know if that's something we all want. Maybe somebody wants to design it with me for fun in a studio in architecture. They would get a kick out of that. But I think as engineers, this is also a huge motivation into how we address the building sector. And one of the best examples right now is if you go to Seattle, the Bullitt Center, it's one of the first living buildings. It's both net zero energy and net zero water. So it produces, by catching water and electricity on its roof with PV panels, enough to sustain itself on the average over a year. But the problem with this building, right, is that large roof. If I take this building into the architecture school and we start talking about it, I have a big problem. A lot of them just say, this building's ugly, and it's not ugly for just pure aesthetic reasons. I look at it and think it looks pretty cool, because it's kind of like, I like engineering things, I like bicycles, equipment, a lot of equipment there. But architects aren't so excited about equipment. And if you're going to have a building that wears a hat, you better have a pretty good reason why the building's wearing a hat if you're an architect. And it can't just be because you want PV panels and to catch water. There has to be some sort of design motivation that's really powering their project. And understanding that is really the part that my engineering side struggled with for a long time, is that there are rational arguments that don't have to do with numbers and figures and data for why things get built and why we do certain things. And I think that really rings true in this idea of behavior and how we as a society also need to understand all the different aspects, both the engineering and the aesthetic and the design components, and how those all blend together. So the first place that I finally started to account for both these things was when I went to Switzerland and did my PhD in the architecture school in the Institute for Technology, and then moving on, continuing to work for the ETH in Singapore, and really taking these two disciplines and figuring out what was one way that I could talk to both of them. And the funny thing was, we ended up not making things simpler, but actually making things more complex. And so when I arrived here, we continued that theme, sort of in this idea of the chaos lab, because chaos isn't just an acronym, as Peter mentioned, which also I think Ellen demonstrated quite well yesterday that acronyms are effective tools at communicating very quickly a project scope. But for me, the acronym Cooling and Heating for Architecturally Optimized Systems is just the tip of the iceberg. And really, chaos for us also represents this idea of thinking beyond the simple energy balances in buildings and the simple mindset of how buildings operate. So it has to do with entropy and this concept of combining the entropy and the second law of thermodynamics, how things dissipate into the environment, with the idea of energy balances. The simple thing that we do to figure out how energy efficient buildings are is balance the amount of heat that we put in and the amount of heat that the building loses. And we try and minimize the energy inputs. But there's many steps along that process of bringing energy in and out of buildings that are extremely important. So Exergy as a tool ended up being extremely effective because the interesting thing was when we went and talked to architects about this phenomenon, all of a sudden energy wasn't this boring thing that they had to learn prescriptive metrics for. There was actually a phenomenon and something that was beyond the sort of traditional mindset, which excited them. And we are actually very effective at communicating ideas like simple things about Exergy being the value of energy, right? So we all understand quite quickly that 50 Singapore dollars are not equal to 50 US dollars. And we have a similar problem with energy, right? In terms of energy, we can have 50 kilowatt hours of heat in a boiler and 50 kilowatt hours of electricity. But these things are not really the same. I can do a lot more with 50 kilowatt hours of electricity than I can with 50 kilowatt hours of heat. There are fundamental limitations in the second law of thermodynamics that tell us how much I can extract from certain temperatures in a system. So in general, when we quantified, especially at the district scale, district heating systems and electricity grids, we often just add up joules or kilowatt hours, but we don't necessarily take into account what the temperatures in the systems are. And that's something that I'm working directly with facilities now on thinking about the campus steam system and the district cooling system that we have on campus, about how we can really optimize those in our campus as a lab. And the main part, not to delve too much into the details, is entropy just allows us to create a new part of the energy component where you actually have some loss in the ability to utilize the energy that you have in a system. So you subtract the amount of energy generated in this system. And the main thing to take away from the equations in the system when I apply this to a building, right, is that the temperature differences, as I bring heat into a building, I need to make it warmer so that the warm heat transfers to the colder space. The warm, hot temperatures transfer to colder temperatures. And the Exergy part is really just that temperature difference. And the big take-home message, and which has been really effective both in engineering and architecture, is that if we design buildings just with simple energy balances, here you see a 98% condensing boiler system, and in that case, you have just 2% of the energy lost out of the stack, but all the heat goes into the building. But the difference is, the heat in the boiler is about 1,000 degrees, but the room only needs to be 20 degrees. And so there's a huge mismatch in the quality of that energy. And so the Exergy that was available in that combustion would be much better used for another process that needs that high level of quality in its system. And so for my research, one of the big areas is how we combine systems that bring those temperatures closer together in the systems. And that's why ground source heat pumps are great opportunities. The temperature is much closer to the room temperature than, say, a -10 day outside. And same with the emission systems in buildings. If we use large surface areas and radiant systems like we have here in the Andlinger Center, which I'll talk about later, we can understand how temperature really matters. And that's the big, simplest message that we can deliver to architects and engineers in this context. So I can design the surfaces in this room to emit the same amount of energy as the little diffusers, right, if they're large enough, right, because the heat transfer, the amount of heating or cooling I can give to a room is limited by the temperature difference and the surface area. So if I make a big surface area, I can make the temperature difference much smaller. But unfortunately, this fact that temperature matters is in standard systems problematic. And this was something I experienced directly in Singapore, and we're continuing these thoughts with Elie Bouzaid and Jim Smith in this Sustainable Research Network on urban water in the context of how latent heat transfer happens with all of these different devices. But the main thing in this project was, what do you think happens to the heat from this air conditioning unit? It goes this way, right? And all of these units' efficiencies depend on what the temperature it is outside. But do you think it's the outside air temperature around these units? It's not. And so these guys are working way harder than these guys down here. And the other thing is this whole area also gets hotter, and we have a whole project about back lanes in Singapore that we worked on showing, hey, there's a huge opportunity to not only increase the efficiency, but reclaim this space that nobody wants to be in because it's 10 degrees warmer than the regular temperature outside. And we also then took those systems that are sitting on the wall there, just tacked on that people can buy in any DIY hardware shop in Singapore, And we thought about ways that we could integrate them better into buildings, because even the large buildings and the apartments I lived in still use these standard systems. And so this was a project called the 342 project, which we're continuing now with our group in collaboration with Siemens Building Technology in Switzerland and the ETH Zurich at the United World College in Singapore, where we took the concept of ducts in buildings, which you see on the left, and we actually had an office building that we worked in that literally had 2 meters of space up in the ceiling for all the ducts in distributing the air conditioning in the building. And we were able to show that if we take a concrete slab, and I double-checked with my structural engineers on this, right, Claire? That if I load a concrete slab, the top gets in compression and the bottom gets in tension, but the middle's kind of not doing much. So we can take that out and actually put all the ducts into that space and save enough space in the building to the point where for the 2 floors of the standard construction, I can now build 3 floors with the exact same ceiling height. And on top of that, because we're integrating things into the slab, we also simultaneously integrate piping into the slab that distributes the cooling across that thermal mass, again, distributing the heat through or pulling the heat out of the building, in this case in Singapore, across a large surface area. So it does that much more efficiently for the chillers that are running the system. And in this case, we also explored opportunities to directly integrate the compressors and the air intake systems in the building into the facade structure so that we're not ducting things any further than we have to, which allows us to also create even smaller ducts with less losses. And then when we modeled this in larger high-rise scenarios, and we just had a paper come out 2 weeks ago now in the Council for Tall Buildings journal, showing that we can save, because we diminish all the surface area on the outside of the building. Remember, all those 2-meter spaces also had surface on the edge of the building. We get rid of all that surface, we reduce all of those heat gains. So we save 40% of the cooling energy, we get 20% more office space because we don't have all those ducts, both the vertical chases and the ones running through the ceiling. And as well, we save tons of material and increase the user comfort through this radiant cooling system in the building. So this was the end result of the space that we designed and implemented at the United World College. That they very generously, this is one of the hardest things about just doing research in buildings, is buildings are in fact the most expensive thing someone can buy. And so if you're going to sell someone a building, you're not going to say, I have this thing that I think just might work maybe. We haven't really tested it, but can we put it in your building? So luckily, actually, we found a project manager who was pretty proactive in Singapore, and we were able to actually deploy this project. And here you see these are high temperature cooling panels in the ceiling of the space, distributing the cooling over large surface areas. And we're looking at then, the next step of this is understanding how do we deliver, and I'm sure anybody that's been to Singapore will know about this challenge, dehumidification, because it is humid in Singapore. The temperature is rarely above 85 degrees, but the humidity is always above 80%. And so getting rid of moisture is a big challenge. And the way we traditionally do that is by cooling the air down beyond the dew point and causing the water to condense out of the air. But we can also do this using intelligent chemistry. And so we have been doing a lot of research here with some chemical engineers, and one of the chemical engineering grad students, or one of the students I stole from chemical engineering to convince to come work with me in the architecture side, to develop some new desiccant-based dehumidification systems. So this is an early sketch of a prototype that we built. And also through the e-affiliates, one of the e-affiliates meetings, we met people from Arkema who were able to supply us with a really perfect membrane that's a non-porous membrane, because the desiccant we're working with, which we were able to, through another industry meeting, get from Dow. So Dow has this desiccant they wanted to try out, and then we were able to get this membrane that allows moisture to transfer through it, but keeps the desiccant hidden behind it. So in that way, we can transfer moisture in and out of the liquid without having to have an open or free surface. One of the biggest problems when you try and use desiccants to pull moisture out of the air is you have a free surface, and then the air tends to not just have air in it, there's dust and all kinds of other components. So this is one of the things we're designing right now to try and address this problem, and collaborations with chemistry have taught me an immense amount of things. And this is the point where we started up at a building, and already in my first couple years at Princeton, I had to do like quantum interaction potentials for surfaces when we're dealing with these desiccants. So this is, I think, one of the moments where you can really see the span that happens in the Andlinger Center when you're collaborating across all these disciplines. And this is something we've been having a lot of help from Bruce Cole as well as Jay Benzinger about how these kinetics work in the system and how we can optimize the removal of moisture from the air in buildings. But then my part of the system is to come back and say, okay, the really neat opportunity would be, now let's design something where we have photovoltaics on the facade, and photovoltaics get about 20% of the energy from the sun, at best, converted into electricity from market types of PVs. But then they also generate a lot of heat, and all that extra heat, that other 80% of energy that's coming in, you can use that to regenerate those desiccants. And so it's very nice to think about a system where instead of subcooling air to condense water out, we heat up a desiccant to remove the moisture from the building system. Because what do we have a lot of when we're doing dehumidification in Singapore? We have a lot of heat. So let's use some of that heat to drive our system instead of doing subcooling. And the initial results from the desiccant we're working on are pretty promising in terms of being able to achieve temperatures that are realistic. So we're really excited about that. And I want to jump through one more project, or a couple more projects that are really more on the level of the interdisciplinary nature, and how, in my role, that last part of the project where we design something is really where we get to do this innovation through integration, right? Taking the structural parts of the building and these chemistry equations and bringing them up to a level where we work together. And the probably most representative project of this is the first one that my colleagues Claire White, Dan Steingart, who you already heard, and Barry Rand did on developing a concrete wall as a battery. Because it turns out in a conversation that may or may not have been over beers one day after work, we found out that Claire's chemistry for low CO2 concrete, in fact, is an excellent electrolyte for charge carrying in a battery. And in fact, the rebar in most concrete could also be used as anode and cathode material, depending on which metals you use. And Dan has a whole range of unhappy families that could go into this concrete. So we made a proposal, and it seemed a little far-fetched, but in the end, it all fit together just enough that we were able to do experiments and demonstrate that we could, on the top right there, in fact, store charge in concrete. The biggest challenge that remains now is to keep the charge there. So our battery is even poorer than Dan's poor battery that he demonstrated. But in this case, it's more interesting for me, because then we can actually start building buildings out of concrete that does more than just hold up the building. It also buffers that electricity demand, which is one of the biggest challenges we have in terms of renewable supply in the grid. The other project that I led, which this project and the battery wall were both funded by the Andlinger Center, and in this case, I was leading the charge on an idea about how to combine evaporative cooling with the reflection of radiant heat transfer. And ideally through this, we'll arrive back at the sensors that I'm passing you. The first part, which I'll just touch on briefly, is the idea that you can do evaporative cooling directly on the walls of buildings. And this is something that Elie Bouzaïd in civil engineering and I have been talking about a lot, and thinking about ways that you can encapsulate water in building facades. But in the project that I worked on, we did what's called indirect evaporative cooling. Because in New Jersey, if you buy a swamp cooler, it's not going to help you much in the summer, right? 70% humidity, and that maybe cools the air by 5 degrees, but then it's 100% humidity. That's not much better. But if I take that 5-degree cooler air and do another heat exchange with some air that you didn't add moisture to, now you have cooler air that you can use in your system. And that's what we did in these prototypes that we built that focused on reflecting then that evaporatively cooled, the indirectly evaporatively cooled fluid that we have in the system. And this was the first prototype that my students built in remarkably 2 weeks. Architects are extremely good at fabricating things. And unfortunately, though, we found that the reflection underneath this little umbrella was not very effective, so we had to come up with a better plan, and one that involved more geometry. And this is where really the architects sort of took the lead and helped to develop a geometry where we did a bunch of ray tracing and figured out, hey, if we try and build a parabola in this image, and what we want to do is reflect all the heat off of the people onto a really cold pipe. So you all are emitting heat, and I can make you feel cold if I just surround you with a big, huge chunk of ice, because you'll radiate heat, even if the air temperature stays the same. So the whole point of the project is to absorb radiation from people and focus it on cold things. But we emit radiation in every direction. We don't emit it like a beam. So we had to come up with a way to capture all that indirect, those off-axis rays. So we built a cone so that the light that comes in at different angles all bounces off the cone and hits like this stick in the middle of the cone. And we did some fun optimization of different forms where we found where the ray tracing could focus in a system, but the cone tended to be the best solution. And in an homage to the 1960, the professors of architecture in the 1960s who were doing research on energy and built this device to simulate the sun, we also created a structure. So this was the moment where we didn't just build a building with a hat. We also thought about the architectural relevance for a little while. And this is actually the sun path on the summer solstice, so it shades the space underneath exactly. And then we had to build it. And the process was pretty straightforward, because if you're in architecture these days, you tend to have very fancy equipment that allow you to digitally fabricate very specific forms. And so here we have our industrial robot in the architecture school, which we can program to then make very precise cuts of these cones. So these cones then are formed out of a bunch of blocks using a hot wire cutter on styrofoam. And by having the ability to take that geometry and pack it into these 24-foot-long blocks of styrofoam, which, by the way, I also figured out how to recycle styrofoam, because as a child I was also told, never buy styrofoam, it's bad. You can actually recycle styrofoam these days. So all the offcuts were recycled, and we were able to create 126 of these blocks in a series of 6 different types that then stack together, as you see here, on its back to create all these forms. And as we stack them, we put these pipes in the middle that were coaxial pipes, so there's water flowing down the middle and then comes back, or down the outside and then flows back up the middle. So each of those black sticks are where the evaporatively cooled water goes. And we're able to then generate a system of supply and return that goes to a very small evaporative cooling tower that's located next to the system. So here's the moment of truth. That was the bringing the system down after we put all the pipes up, and here you can see it in its final form, where we then tested the emission of radiation across these different cones that we had created. So as you can see here, is when the cold water is coming into the system, and we're tracking then what the temperature is with, in this case, a small sensor that we developed to be able to see the entire temperature inside of the dome. Because with one of these infrared cameras, one of the biggest challenges is the reason that these cost still a couple $1,000 is that you have to pay for this germanium lens, and that's really expensive to do. And so what we did was, and because of that, you can't build a fisheye lens on an infrared camera. And we built then a new sensor that allows us to see the entire inside of this dome and stitch it all together. And here's the team that helped. This was a group of architects, mechanical engineers, civil engineer, chemical engineers, and in the back there, even a couple high school students that helped over the summer. And the 2 postdocs that work for me, actually, I'm proud to say, are both faculty members now at Berkeley and in Melbourne, and we're still collaborating on these types of projects. And you can see after we had the building set up, we also checked with occupants to see whether it was actually colder. This was a slightly biased occupant who's a farmer from Iowa. I think I know him from somewhere. But we did do a survey, and we actually reached out to the psychology department, Sander van der Linden, made sure that we were asking the right kinds of questions. And this is the official sort of comfort scale. Some of you may or may not have heard of this perceived or predicted mean vote in terms of comfort. But we asked people, and one of the key questions I want you to remember, for those of you that have played with the thermal camera, or the little thermal camera I was passing around, is this idea of what is the temperature you perceive in a space, right? Because this is something that we all think we have a good sense of. But the main result from the survey was that we did have, in fact, a perceptible cooling effect using only evaporation going into these small pipes. So this is a pavilion outside, so by having the cooling only go through these little pipes, we didn't have a large surface area that was actually cold. So the small surface area lost very little of its cooling capacity to the air, But when you stood in there, you had the full surface effect of the radiation around you. So you would feel like you were standing in a space where all the surfaces around you were, in the case of a day where it was 70% humidity outside and 85 degrees, we dropped the water temperature down to 70 degrees, and we were able to distribute that temperature around the space radiatively. So the end result is that we built this sensor that not only does, that we're working on now today, so a spin-off of this, which we've now patented this little device that does not only scanning of the temperature in the whole space, so it adds up all of these temperatures, but it also does range finding with the LiDAR sensor. And so we're able to see both the temperature inside the dome in a full 360-degree view, and we're also then able to plot that in space. So with one scan of the system over 5 minutes, of a room over 5 minutes, we can see the whole system. And this is something now that we're working on developing as a device both for fault detection in buildings or for diagnostics in buildings, but also as something that can replace the standard thermostat in a building that only measures the air temperature, right? Because remember in our survey we asked what temperature do you think the room is? Well, a building only thinks about the air temperature. It never thinks about that radiant temperature of its surfaces. And these types of devices allow you to scan the room, and this is another one of the rapidly prototyped versions as I hand it around. And this one will look at the distance of the system, but the one I passed around will be able to plot the room space in a small enclosure located on the wall, producing this type of result, whereas if I have in an existing building, I know the geometry of the room, and so I can produce this data just using a sensor that looks at the room. And with the LiDAR one, this was produced directly where that little device sits in the middle of the room, scans around it, and produces instantaneously the geometry of the room and the temperature of all its surfaces. And this is very valuable because as we demonstrated with the thermoheliodome in a very extravagant form, radiant surfaces are really important in buildings. And this does apply to real buildings, this very building here. This building has radiant cooling panels and a lot of thermal mass. And both those things, thermal mass, in this case all the concrete in the stairwell, and the radiant panels in the hallways, that's what you see above you, those metal panels all have copper tubing behind them. And what that does is both the thermal mass and the radiant cooling, they're able to maintain their temperature at a much more constant level. And so by doing so, we can skew your perception of the air temperature. Because in fact, you are all very, very bad temperature sensors. You're really good heat flux sensors. What you can sense, right, unfortunately our beautiful chairs don't have any metal on them anywhere. But if you touch metal, right, it feels cold, even if it's the same temperature as the table or chair that you're sitting next to, right? And you feel that way because you sense the rate of heat loss. And I can change the rate of heat loss from your body with my thermoheliodome or with the radiant cooling panels in the Andlinger Center. And so our building is, in and of itself, this great campus as a lab project where I can see in action some of the types of systems that I'm researching. And I can also then look at the data from our thermostats, and in our very own space, graduate space, we're able to show how this works. So to wrap up, the ability to use our own building and to have my own graduate students be able to deploy this very sensor and then show to all the grad students that are with them in the space, this is why we feel cold, even though the air temperature we're measuring is 70 degrees. It's very, very promising, and it provides us a really rewarding direct feedback, right, to be able to work in our own environment and develop new tools that help and engage directly with our colleagues and in the buildings and the campus around us, where our research can be deployed sort of in an immediate fashion, which is a very unique opportunity, I think, and one of the best things about being at the Andlinger Center. Thanks.
Thank you, Forrest.
Yeah.
Why don't we take a few short questions?
Hi, nice talk, Forrest. Barry Rand from Electrical Engineering in the Andlinger Center. In the 3-for-2 project, I just wonder, when you embed all these things in a very narrow slab of concrete, you have issues with maintenance and repair.
Yeah, so all the ducting is very close to the facade, so the short runs of ducting are actually much easier to maintain than the very long runs that also tend to have much more roundabout ways to get around slabs and structures. So in fact, these shorter, smaller ducting systems, which need to sometimes be cleaned and filters changed, are a little bit more accessible than sometimes the standard systems. So in some senses, if a duct has an issue in a large-scale building, it's largely due to the fact that it's exposed too. So you also are protecting some of these systems by embedding them more in the structure rather than having them hanging out, usually sort of from the ceiling in these exposed spaces. But it is also a challenge to make sure that the resiliency of these systems is still something that's going to last for a long time. Because buildings, when we put these systems in a building, they need to be able to be there for 50 or 100 years if they're embedded in there. So that's one of the sort of critical components of understanding the application.
Yeah, I have a question about the heat flux issue. So before air conditioning existed during the Raj in India, it became customary for business people to wear cotton safari suits, essentially, shorts and short-sleeve shirts among British everything, business people, diplomats, everything, and you still see that in Africa. In this country, for some reason, the culture is to wear wool suits in the summer in Manhattan if you're an attorney or a business person. And so we have to refrigerate the buildings to 68, and you freeze to death if you dress appropriately for the season. Mm-hmm. So my question is, with respect to your heat flux statement, the other thing that affects heat flux is insulation and actually a visible barrier to infrared, which a wool suit is. I wonder if there wouldn't be a multiplier effect by getting people to wear shorts.
Oh, yes.
Not just that you wouldn't have to cool the building to 68, you could maybe have it at 72, but
Yeah.
you could in fact have it at 78.
Yeah, no, behavior is a huge aspect, and this is actually one of the recent programs at ARPA-E was this distributed local thermal amenities. I think it was called Delta, and the project was specifically that. How do you change the air temperature and maintain thermal comfort on people? And some of the projects were about actually heating and cooling clothing, right? There was like the direct application, and then others about the radiant heat exchange. But the thing I didn't get to, because I can talk a lot about thermal comfort, is there are 6 different factors that are influencing your thermal comfort, and temperature is the one we most associate with. And then there's also convection. So if I move the air around you, I also make you cooler. But that has certain limitations. And then there's the humidity level that also changes the rate of evaporation from you. And then there's these other 2, which you alluded to. One, clothing. So in these comfort models, you have a clothing level. It's called a clo, is the unit, a unit of clo. So 1 clo is like a regular dress. I think a suit is 1.3 clo. It's in there. There's a Danish researcher who's very famous that did all this research in the 70s named Fanger. And then the other one, which you didn't mention, is metabolism. There's a MET unit also, which a standard unit is 1 MET. And these are basically scalars in these comfort models. And after you eat, your metabolism always goes up. So you could also start to think about designing the systems in buildings to react to even metabolic rate. And that's one of the things we're super excited about building these sensors, because if I could have done the live demo, which didn't work, I took a picture and you can see all the people being warm, but I can also see where you are. And these motion sensors, like this guy that many of you probably have in your office, that only work on motion. I don't know how many people have had to like jump up and like do a jumping jack to get the lights to go back on in your office. If I use a temperature sensor, I can see like hot people in the space. I know you're there. And I also not only know you're there, but I can see if your skin temperature starts to go up and down. So we're working on with some colleagues in Italy and in Japan that do these human body models to actually start to develop metrics around thermal comfort directly related to skin temperature, and it's a human body exergy model of what is the rate of exergy destruction in your body, and trying to optimize this numerically. So trying to get beyond just these sort of scalars of 1 MET and 1 clo factor, but they are very, very important. I'm super glad you brought that up, because I mean we often just think about the temperature in the space being like, how can you turn the thermostat down or up? And it's so much more than that.
One last question.
I'm a resident. Didn't you miss a factor? Namely, drink ice water
Definitely, yeah. Usually, I mean, that's with the metabolic, your metabolic, core temperature is the thing that's really driving all these heat transfers. So that's really important. And I didn't actually say radiant exchange was the most important one. Obviously, that's what I'm doing research on. But yes. So yeah, if you have any questions about how your body doesn't sense temperature, you can find me at lunch, and you can tell me how much hotter you are after you eat lunch.
Thank you, Forrest.